The cache operator is very useful under two circumstances. The first is a very common one. You've built a particle flow, and due to its complexity, calculating its particles over, say, 200 frames can take a while. When you try and scrub the timeline to frame 150, let's say, there's a big delay. And that's because it has to calculate all the particle data between frame 0 and frame 150. Once it's done that, you end up with a display in the viewport. So let's actually do that now. If I scrub up to, let's say, frame 70 here, you can see I don't see particles. There's a percentage being calculated here, and it's actually calculating all the simulation between this point here and this point here. And you can see I've got a kind of firework display going on here. I've got real time turned off, and if you actually have real time turned on, that can actually highlight one of the reasons for using the cache, because you'll get absolutely awful interactive playback. That's because it's trying to maintain a frame rate of, let's say, 30 frames a second. So it'll skip onto frame 10, then onto frame 60, then onto frame 100, and it will actually try and calculate the particles in between, but it won't ever get to that point. And so you'll find you'll basically get one frame, appearing every say 30 frames or so. So it's not really very useful. If I have real time turned off, it'll play every frame. So if I press play, you can see it's calculating each frame, and the time to calculate each frame is less than a second. It looks like it's maybe doing 2 or 3 frames a second there, so it's actually not too bad. You can see that once it's played through once, it's playing through again, and there's no real sort of speed difference between the two. So another thing that you'll notice is that if I stop it at this frame and I want to go back a frame, it's only actually gone back a frame, but there's a really big delay, and that's because it's actually caching. It's calculating the particles all the way from 0 back up to 79 again. And you can see I actually moved the slider a little bit too much, and it's actually going on to it looks like frame 78, and it's calculating all the particle data again. So that can get really, really tedious when you're working with a large amount of particles. Okay, let's see the cache operator in action now. So I'm just going to put it back to frame 0, and you can see I've got a cache operator set up here, which I've got turned off in the moment. I'll just turn that on, and I'll make sure it's clear of any data, and I'll just press play. And there you can see our simulation is playing, and you should find that it doesn't actually play any faster than it did previously. That's because it's actually going through every single frame, and it's actually caching the particle information for every single frame as it goes along. Now, when it gets to the end of the timeline, it'll start to play again, but you should find that this time the playback is actually much faster. It won't be incredibly fast because it's actually got quite a lot of particles to display anyway in the viewport. But there you go. You can see it's actually relatively fast, and that's because obviously it's cached all the particles. Now, if I stop the playback and I say I move it up to frame 90, you'll notice there's no delay. And that's obviously because it's actually cached all the particle data. I can go backwards, so I can have our particles, there you are, they flow backwards into the source, out again, back again. So you can see now that you've actually effectively, recorded, as it were, your particles to tape. In other words, you've kind of baked them, and that gives you sort of interactive playback. Now, the second circumstance that you would have to use a cache in is that, let's say you have to network render your particles, and you want to ensure that there's no random disparity over the network due to differing processor architectures. Because it's been a problem in the past that if you used a chip by, say, Intel, and if you used another chip by AMD, the floating point unit in those two chips use different architectures, and that means that for any one math problem which is given to the processor, you may get back a very, very slightly different result. Now, that very slight difference in result would normally not make much of a difference, but with particles it could actually mean that particles rendered on one processor will follow one path, and on another processor they'll follow another